Hello, and welcome to this video on the alveolar gas equation. What is the alveolar gas equation? The alveolar gas equation allows you to calculate the alveolar partial pressure of oxygen. In order to be able to do this, you need to know the following values: the inspired pressure of oxygen and the alveolar pressure of carbon dioxide. In addition to this, you also need to know the respiratory quotient, as seen here. How is the inspired pressure of oxygen calculated? The inspired pressure of oxygen is different from atmospheric oxygen because it is warmed and contains added water vapour. Barometric pressure falls with increasing altitude, roughly halving every 18,000 feet. However, the partial pressure of water vapour remains constant at 6.3 kilopascals. Therefore, this is the equation which allows you to calculate the inspired pressure of oxygen. The inspired pressure of oxygen equals the fraction of inspired oxygen multiplied by the atmospheric or barometric pressure minus the pressure of water vapour. So why is it relevant that the barometric pressure falls with altitude? Well, at sea level, the barometric pressure is 101 kilopascals. In order to calculate the inspired pressure of oxygen at sea level, we put in the following values: a fraction of inspired oxygen of 21%, as we see here, a barometric pressure of 101 kilopascals, and a partial pressure of water vapour, which is constant, of 6.3 kilopascals. Therefore, at sea level, the inspired pressure of oxygen is 19.9 kilopascals. However, at an altitude of 63,000 feet, the barometric pressure is 6.3 kilopascals. Therefore, if we substitute again the values into the equation, the FiO2 will be 21% again, the barometric pressure 6.3, the partial pressure of water vapour 6.3, therefore the inspired pressure of oxygen will be 0 kilopascals. At 63,000 feet, barometric pressure is equal to the partial pressure of water. Another way of putting this is to say that at an altitude of 63,000 feet, water boils at only 37 degrees. What is the respiratory quotient? It is the ratio of carbon dioxide produced to the oxygen consumed. Here are the values for the following metabolic substrates. The metabolic substrates are the main determinants of the respiratory quotient. Okay, so now we will go back to the alveolar gas equation. Now that we know how to calculate the inspired pressure of oxygen, as we discussed on the previous slide, we can start by substituting that value into the equation. So at sea level, we have an inspired pressure of oxygen of 19.9 kilopascals. We will assume an alveolar pressure of carbon dioxide of 5 kilopascals and a respiratory quotient of 0.8. Therefore, at sea level, we calculate an alveolar partial pressure of oxygen of 13.7 kilopascals. However, we can do the same for an altitude of 30,000 feet, which is the height of the peak of Everest. So at an altitude of 30,000 feet, the barometric pressure is 30 kilopascals. So by substituting that into the equation, we calculate an inspired pressure of oxygen of 5 kilopascals. So now we can substitute this into the alveolar gas equation. So now we have an inspired pressure of oxygen of 5 kilopascals. For this equation, we'll assume an alveolar pressure of carbon dioxide of 3 kilopascals. This is because at an altitude of 30,000 feet, the majority of us would need oxygen, but for those who would be able to survive at the top of Everest, they would be hyperventilating, and therefore we will assume an alveolar pressure of carbon dioxide of 3 kilopascals, and again, a respiratory quotient of 0.8. So by working through this equation, we end up with an alveolar pressure of oxygen of only 1.25 kilopascals. Why may the alveolar partial pressure of oxygen differ from the arterial partial pressure of oxygen? If the inspired partial pressure is held constant and the arterial CO2 increases, the alveolar pressure of oxygen and arterial pressure of oxygen will always decrease. The alveolar pressure of oxygen is a calculation based on known or assumed factors. However, the arterial partial pressure of oxygen has a maximum value defined by the alveolar pressure of oxygen and a lower limit determined by the following: VQ imbalance, pulmonary diffusing capacity, and the oxygen content of blood entering the pulmonary artery. In particular, the greater the imbalance of the VQ ratio, the more the arterial pressure of oxygen tends to differ from the calculated alveolar pressure of oxygen. What is the normal alveolar-arterial gradient? The alveolar-arterial gradient varies with age and with the fraction of inspired oxygen. Up to middle age, breathing ambient air, the normal alveolar-arterial gradient is approximately 1.3 kilopascals. This means for an alveolar partial pressure of 13.8 kilopascals, the arterial partial pressure of oxygen would be 12.5 kilopascals. With a fraction of inspired oxygen of 100%, the alveolar-arterial gradient ranges up to about 10 kilopascals in a normal healthy patient. If the alveolar-arterial gradient is increased above normal, there is a defect of gas transfer within the lungs. This is usually due to VQ imbalance. Common causes of an increased alveolar-arterial gradient. 1. VQ mismatching. Blood flowing through high ventilation perfusion areas with a higher partial pressure of oxygen cannot compensate for the blood flowing through low ventilation perfusion areas. For example, pulmonary embolism will cause a high VQ ratio. This is where there is ventilation of part of the lung but impaired perfusion, and this is termed dead space. On the other hand, severe asthma will cause a low VQ ratio. This is where there is impaired ventilation but normal perfusion, and we call this shunt. In severe cases, both of the following will cause hypoxia. Number 2. Diffusion impairment will also cause an increased alveolar-arterial gradient. This may occur in conditions such as pulmonary fibrosis and pulmonary edema, and will also occur if lung capillary transit time is greatly reduced, as we see in exercise. And 3. Anatomical shunt. This is an extreme form of VQ mismatch where deoxygenated blood enters the systemic circulation. This is seen in patent pheromone ovale. We will now look at how minute ventilation affects the partial pressure of alveolar oxygen and alveolar carbon dioxide. As minute ventilation increases, arterial CO2 and alveolar CO2 decrease. Arterial CO2 approximates alveolar CO2 due to the rapid diffusion of carbon dioxide. There is a reciprocal increase in the alveolar pressure of oxygen. We also see on this graph that as minute ventilation decreases, the opposite will happen. So at a minute ventilation of less than 1 litre per minute, the alveolar partial pressure of oxygen will be less than 3, and on the other hand, the alveolar pressure of carbon dioxide will be around 15. Thanks for watching this video on the alveolar gas equation.